discuss. So last class we have discussed about the topics, course outcome, program outcome, and what are the topics we'll cover in this course. Everything is discussed, and we have seen the first starting point of your course is PN junction diode. But I told that I'll take some classes regarding the semiconductor material property and types. Okay, what you have discussed or studied in the intermediate level. So we'll start from very basic atomic structure. If you take any material or solid, the smallest particle is atom. So if you understand from that part, then it is very easy to understand all the concept consequently. So if you take any atom, what is present inside that? Nucleus, and inside that nucleus, neutron
and proton.
and proton. Okay, neutrons are neutral and protons are positive charges. So at the center, that is present as nucleus, and around that, in elliptical orbit, lot of orbits are there, and in which the electrons are revolving, and these electrons are having negative charge. Okay, so if I take, this is my first orbit, it will have certain number of electrons which will be described as 2 to the power or 2n to the power 2, 2n square, where n is the number of orbit. So if we take first orbit, so this is the first orbit, this is the second orbit, this is the third orbit. So first orbit means 2 into 1 to the power 2, that is 2 electron. Second orbit, 2 to the power 2, that is 8 electron. Third, 18, like that it will go. Okay, so you can see in the first orbit we have 2 electron, second orbit 8 electron, like this, 4, 5, 6, 7, 8. Similarly, in the third orbit we can have 18 electrons, which is shown here, and I have written here, atoms consist of positive charged nucleus and electrons are revolving around them in different permitted orbits. And how many number of electrons are placed in an orbit, that is decided by this equation, that is 2n square, where n is the orbit number. You can see nucleus consists of neutron and proton, and these are the electron cells, and these are the electrons which is shown here. This is the Bose postulate. I think many of or almost all have studied these things. Yes or no?
Yes, sir.
Yes, sir.
Now, if we are giving some energy here, or the electrons which are present on these orbits can gain energy, and by gaining energy they can be excited to higher orbits. Suppose this electron gain energy, it will go to this next orbit. If this electron is gaining energy, it will go to next orbit. If this electron will gain energy, then it will come out of this orbit or come out of the atom. Basically, the logic is that when electrons are gain energy, they go to higher orbit, and when they lose energy, then they can go to the lower orbit corresponding to where they are placed. Okay, so electrons jumps higher to lower to higher orbit by gaining energy and fall back to the lower orbit by emitting energy. So that energy can be the form of light or heat, anything. Okay, in forward classes we'll see how these energies or the materials will provide you light or heat, or what are the different type of material which are giving you light and heat, so that we can use those things in different application. Like if you consider a light emitting diode, there we are getting light whenever that electrons from higher energy to or higher orbit to lower orbit, it will come by radiating energy, that energy in the form of light. So visible light we can see, and that's why these LEDs we are using in day-to-day life. Okay, so these are the basic fundamental things, atomic structure and how the electrons are placed in orbits, and when they are jumping from one state to other state, then energy by getting energy, and when they are losing energy, they will fall to the next immediate next or lower orbit. Is it clear?
Yes, sir.
Now, once you understand that basic thing, then we can go for energy level and energy band. So first we have to understand what is energy level. Now, if I take an atom, this is the nucleus and this is the orbit, and some electrons are present here. Let us take, these are the electrons present here. Now, around this atom, I'm not finding any other atom, so I can say this is isolated atom. Isolated atom, because it is isolated from other atoms. Near to this atom there is nothing. Now we can see the first orbit have 2 electrons, second orbit have 8 electron, third orbit have some electron, and each electron having some energy, because that's why they are placed in that orbit. And fundamentally, whenever the nucleus is there, the positive charges present in that as a proton, they'll attract these electrons which are revolving around the fixed orbit. That's why they are stable. They will not fall to this nucleus. Otherwise, it will fall to the nucleus and the system will collapse, atom will damage. So there is a attraction of this electron, this nucleus on this electron, and you can say each electron have some energy. Now when I'll constitute, or I'll just check the first orbital energy. Let us say in general you are measuring, or what is the unit of energy till now we are using? How you are Joule. But here we'll take another unit which is called as electron volt. Okay. In electronics we are not using joule as a unit of energy, we'll use electron volt. That means if I move an electron in a 1 volt potential field, how much energy is gained by this electron is called as electron volt, and this is the generalized unit of energy in electronics. Mostly we'll use electron volt, not joule. So if I take the first orbital energy, or the energy possessed by these electrons in the first orbit is, let us take, I'm just for your understanding, any arbitrary number I'm taking, it is not practically sound. So let us take, this is 2.1 electron volt. First orbital energy, or the electrons which are present in the first orbit having energy 2.1 electron volt. Second orbit must be higher than this one, because whenever the energy is consumed by these electrons, they are moving to hash state. So let us take, that is 4 electron volt, and third orbit energy, let us take 6 electron volt. This is just arbitrary number I am taking. Okay. Now, how I can represent this energy labels or energy in terms of a diagram? I'll show you. I'll take x-axis and y-axis, and let us take this x-axis or horizontal axis is the distance from the nucleus. Okay. As I move from the nucleus to upper band, like here, first orbit, second orbit, third orbit, let us take this is R1, this is R2, this is R3. At R1, I am having a energy level that is from first orbital energy, that is 2.1 electron volt, and this distance is R1. Are you getting my point?
Yes, sir. Yes, sir.
Now, if I want to represent second orbital energy, then I'll represent here, that is 4 electron volt, and the distance from the nucleus is R2, and R3 is the distance from here to here. You can write here, or here you can also write like R1, R2, R3. So R1 is from here to here, R2 is from here to here, R3 is from here to here. Reference to the nucleus, and this is here 6 electron volt, and this is the unit of energy. So energy in electron volt you can write. Right. So as I move from the nucleus, the energy is increasing, but at the same time, the force of attraction of these electrons or the force of attraction of nucleus on these electrons are decreasing. Right. The way the nucleus is attracting these first orbital electrons is very high, and the second orbital electrons will be less compared to first. Third is still less compared to first and second. Yes or no? Like practical example, if I give in a class, because last 2 years you are not coming to class, but you can remember when you are in class, those who are sitting in the front bench, always the teacher is focusing on them, because the eye to eye contact is there. And as the student, the number of rows are increasing, their focus is decreasing, and students generally less attentive to the class because they are little bit distance. Yes or no? Am I audible?
Yes, sir. Yes, sir. You are audible.
Yes, sir, you are audible, sir.
Yes, sir.
It should be interactive. Okay.
Okay, sir.
Communication is very difficult. I cannot see you because I am focusing on my screen, and if you are not responding, then I cannot proceed. It should be both way communication. So, as the radius increases or number of orbits are increasing, we are moving far away from the nucleus. The nuclear force of attraction on these electrons are decreasing, though the energy of these electrons are increasing. And in other way, you can say these electrons are most unstable. They are not stable. Okay, they are not stable. So this energy level diagram, the diagram what I have drawn here, this is called as energy level diagram. Is it understood all?
Yes, sir.
So you can see this is the energy level diagram what I have shown here. This is the individual atom, and this is the energy level diagram. And you can see 1s, 2s, 2p is written here. So this is the first energy level, this is the second energy level, this is the third energy level, and you can go with that. Now, once you understand this energy level, then we can go for energy band, because everything is when I go what is the logic why I have explained this one, because how we can differentiate this semiconductor with respect to conductor and insulator, that lies with this energy band. With respect to energy band only, we'll explain that one. That's why I have explain energy level, then we'll see how this energy level is different from energy band. Then we'll proceed to different type of semiconductor. So energy band means compared to this isolated atom, let me take here. Suppose this is atom 1 and this is atom 2, N1 and 2. Okay, here with the first orbit, second orbit, first, second, here also 2 electron, here let us take 4 electrons are present. Same atom means both are identical. Okay, now if only one I am taking, then this is isolated, but now I am taking 2 atoms closely present. That means it is not a isolated system. The effective of first atom will affect the second atom, and second atom will affect first atom. Why? Because whenever they are present near to them, they will interact with each other. Like suppose one person is sitting ideal, nothing is there, mobile is not there, and no person is with him, then he is sitting silently, he is thinking something on his own. But if 2 person will sitting inside a room, definitely even if they are not friend, they try to become friend, they will talk each other and they will try to interact with each other. Yes or no?
Yes, sir.
Now in a solid means which is hard, and in a solid these atoms are closely packed like this. So whenever we take obviously some bonds will be there, and we have not seen those bonds, so I have not explained those things. So let us say these are the atoms present in that solid. Now whenever a lot of atoms are present inside that, there are different interaction forces will acting with each other, like atom to atom interaction force or interactive force, molecule to molecule interactive force, and these different static charges. All these things are combinedly affecting and they will interact with each other. Now come to the level, energy level. Whenever if I want to plot energy level diagram of this atom, first atom and second atom in a single diagram, let us see how or what changes will from this energy level diagram. So let us say this is my energy level diagram where I want to plot the energy level of first atom as well as second atom. So whenever I'll draw the energy level like this, I'll draw. This is for first one and this is for second one, and both are identical atom means the energy level are same. Suppose this is 2.1 electron volt, this is 4 electron volt, here also 2.1 electron volt, and here also 4 electron volt. But when I combine both these things, whenever it is in a same structure or solid, then it is little bit different. Why? Because when I plot these two things in a single graph or in a single solid, then we have to follow the conditions or the theory which already we have studied, the Pauli's exclusion principle. Anyone remember that? Pauli's exclusion principle?
No, sir.
No, sir. Sir, that excitation energy it need to
No.
or
Electrons are kept in orbitals opposite.
So the quantum number can be same for two atoms.
Yeah. That means no two electrons should have same energy level. Okay. Suppose I'll say this is the first atom electron, first orbital atom electron, which is having 2.1 electron volt, and this is identical to that is also 2.1 electron volt. But when it is in a solid, then both the electrons, means 4 electrons are present there, and these 4 electrons placed in first orbit. Yes or no? First 2 electrons in first atom, 2 electrons in second atom, but both are in first orbit itself. So this first orbit electron can be represented like this 2.1, but as both are different atoms, they cannot be placed in a single energy level, because that violate the Pauli's exclusion principle. It says no two electrons can stay in a single energy level. Obviously, spin is different. For first one it is like this, you are representing. Second one it is like this. So when we are combining, it should not be having exactly same energy. So what happens, they will just differ the energy level. That means if it is 2.1 electron volt, it will be 2.10000001 electron volt. Now you see, this value and this value are almost same or not?
Yes, sir.
But they are not
Yes, sir.
exactly same value.
No, sir.
So that will give an idea, means it is not violating the Pauli's exclusion principle, and we can represent both the energy levels in a single diagram. So if you represent the thing, let us take this is 2.1 electron volt, it will be just above that one, like this, 2.1000000001 electron volt. So two atoms I have represented here, which will accordance with the Pauli's exclusion principle. Okay. Now, if it is a system having two atoms, for an example I have shown, if it is 100 atoms or 1000 atoms or 10 to the power 23 number of atoms, then instead of this two value, we'll get this many number of values or not, labels, and everything is closely packed. So if I represent all these things labels like this, very closely packed with each other, but it is not exactly equal, then I can get a range of value here. Suppose it is 2.1 and it is 2.11. Okay, so within this range, let us say 10 to the power 23 number of labels I'll find. So it is, instead of energy level, we'll say this is energy band, because this is the band structure. Are you getting my point?
Yes, sir.
So this is the first energy band. So for first orbit, this one. For second orbit, I can represent like this. I'm not drawing inside that. Let us take this is E2 and this is E1. So first orbit or first energy band, second energy band. Similarly, if we'll have third orbit, then third energy band, like that it will move. So the basic idea is, you can look at here, when it is isolated atom, we represent the energy with respect to nuclear distance, that is energy level diagram. When it is combined or number of atoms are there inside a crystal structure or solid, then the energy level is turned into energy band diagram. And these are the energy band. This is the first energy band, this is the second energy band, this is the third energy band, like that we can represent. So this is the energy level diagram, this is the energy band diagram. And why, I have explained here. For everyone it is clear?
Yes, sir.
Yes, sir.
Now let us see. So again it is shown here to give you an idea how these bands are named. So if you look at the first figure, the nucleus you know, electrons you know, one thing you need to know, these outermost shell electrons are very loosely bound to the nucleus and they are having very high energy and unstable. And these electrons are called as valence electrons. The names are valence electron or outermost shell electrons. Okay. Now, in the second figure, you can see the second energy band is written here. The first one will be below to that, which is not shown here. This is the first energy band, and this is the third energy band, because this is the first, second, and third orbit. 3 orbits are shown here. So first energy band, second energy band, and third energy band is shown here. And the valence band, valence electrons which are present in third orbit are known as valence band or valence energy band. Right? The range of energy possessed by the valence electron are known as valence energy band. In general, energy is silent. We are saying valence band or VB. It is represented as VB. So if I represent that one here, for this example, this is the first energy band. Let us take this is E1. For second energy band, this is E2. This is the third energy band. This is E3. And this is the valence electron or outermost shell electrons. Those are called as valence band. This is the unit energy and this is the nuclear distance. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now the electrons present here, I can represent like that. Okay. Here also you can represent like this. Here also you can represent like this. Now, you know, these electrons are very unstable. Whenever I'll give some energy to this atom, then these energies will be supplied to or captured by these electrons. Now, this electron or first orbital electron, second orbital electron, and third orbital electron, which will who are more prone to unstableness? Can anybody say? Out of this first, second, and third orbital electrons, which are more unstable? So third or outermost shell. Whenever energy is supplied to this atom, right? So they are most likely to get energy and try to escape from the nuclear force, because the nuclear force of attraction on these electrons are very less. Are very less. Suppose you are staying in home, your parents are watching you every day, and if you try to go outside, you have to take permission. But if you are outside home, then you can easily go to somewhere like watching movie and all, and you just have to inform them. Yes or no? So like that also, these valence electron or outside or outermost shell electrons are very unstable. The nuclear force is very less. So whenever energy given to the atom, first they will respond, they will catch those energy and try to escape from the atom. Once they are escaping from this atom, suppose this atom is escaped from outermost shell, they become free. That means there is no nuclear force on this electron. It is not restricted to attach with the nucleus, so it is free. So it can move freely inside this structure. It is free now. Okay, so these are called as free electrons, and due to this free electron, suppose I'll take a material or solid and I'll find a free electron, then these electrons movement will give you current. What is current? What is the definition of current? You know?
Flow of electrons.
Flow of electrons.
Flow of electrons. Till now you know, but the electron till now you don't know what is bound electron, what is free electron. Just now I explained here, the electrons which are attached to the nucleus, they are bound to the nucleus and they are called as bound electron, and if the electron is free from the nuclear force, then that is called as free electron. Now tell me, the moment of or the current is due to what? Moment of free electron or moment of bound electron?
Movement of free electrons.
Free
Moment of
electrons.
free electrons. So if I am giving some potential here like plus minus, so this is minus, this is plus, and this is electron, and it is negatively charged. So obviously the negative force will push this electron towards the left side, and this positive voltage will attract these electrons towards the left side. So finally the movement of electron is from here to here, so that current movement will be left to right. So the electrons which are coming out of this atom, they are free, and actually they are participating in the conduction process of the material, or current due to these free electrons are possible. That's why these electrons, instead of free electron, they are also called as conduction electron. Free or conduction electron. And the energy possessed by these conduction electrons will be, should I represent here or here? Means above the valence band or below the valence band?
Above, sir.
Above, because
sir.
they have gained some energy and they have out of this atom. So obviously the valence band will be, conduction band will be above the valence band, that is here. So you can see here the conduction band is above the valence band, which is shown, and here also this is shown. But the gap between this valence band and conduction band you must know, because whenever we try to escape this atom, escape this, or try to remove this electron from this nuclear force, then we have to spend some energy. So the amount of energy which is required to provide such that this atom, this electron, outermost cell electron will come out of this atom, is called as forbidden energy gap. For silicon, you know, do you know how much energy we should provide so that electron can be released in silicon atom? Don't know. So this is written here 1.1 electron volt. So this is your Eg, and this is for silicon 1.1 electron volt. That means I have to spend 1.1 electron volt. After that only this bound electron will be come out from the atom, and it will become free, and it will give you the conducting property of the material, right? So the range of energy possessed by free or conduction electrons are known as conduction band, which is above the valence band, and the separation between this conduction band and valence band is known as energy band gap. No electron can stay in this forbidden energy gap. That's why it is called as forbidden. That means no electron can stay here. Either they can stay in the valence band or they can stay in the conduction band. Once they are acquiring 1.1 electron volt, they will jump to the valence band, conduction band from the valence band. Until they will not get that energy, they will stay as it is in the valence band. Is the concept clear?
Yes, sir.
Yes, sir.
So atomic structure, energy level, and energy band we have studied, and based on this energy band we can classify the different type of solids. So you already know what do you mean by insulator, semiconductor, conductor, but based on the energy band diagram we will discuss here. So insulator means, the general definition, you know, the material which are not allowed to flow the current through it, they are called as insulator, like paper, glass, wood, all those things. So here if you compare the insulator, the main logic here, the energy band respect. So out of this you can see first, second, third, as you told, most unstable state or unstable electrons are present in the valence band. So whenever we provide energy, first they will react, or they will go to the upper state, or they will respond to the energy. So instead of doing all these first, second, third orbital, we always try to squeeze the diagram, because it may look complex. So we represent the diagram in simpler manner, and we always include valence band and conduction band. So you can see here in this diagram, the third diagram, whatever I have shown here, only two things I have drawn. One is valence band, one is conduction band. That does not mean that other lower bands are not there. They are present, but our effective knowledge or effective representation will be only valence band and conduction band. Okay, you can skip the lower band because they are not participating in the jumping of electrons from one orbit to other orbit. Okay, so if I want to represent those things here, then this is my valence band. Let us say the other bands are drawing like dotted lines, so maybe lower bands are present. Okay, and here I'll represent the conduction band, right? And this is your EG, that means forbidden energy gap. Now, what it says, for insulator, this gap is very high and it is almost near to 15 electron volt, right? Almost 15 electron volt, so that even if I'll provide some energy here, these electrons present in the valence band try to move from here to here, but the physical property of the material is not allowed. Whenever I'll supply this much of energy, then obviously the valence band electron will try to move to conduction band, but during that process the material property will not support to that. That means like a paper, if you try to heat it, what will happen? If you take a paper and try to heat it up, then what will happen?
It will burn.
It will burn.
Yes, sir.
Physical or material properties not supporting to that. When I provide around 15 electron volt, that much of energy, then it will burn. Even you can take wood also, all those things, it is not supporting to that much of energy, so we cannot try or remove the electrons from valence band to conduction band. That's why I say they are not allowed to flow the current through them. Okay, and you can see here unit of energy, what already I have explained. An electron moving through 1 volt potential difference gain some kinetic energy, which is expressed in 1 electron volt, and that can also represent as joule. So nothing but EV means electron and potential. So charge of electron is 1.6 into 10 to the power minus 19 into 1 volt. If you calculate that one, you will get that much of joule. Okay, but standard unit we are taking as electron volt, but you can also express that one in joule. Clear?
Yes, sir.
Yes, sir.
Now same way you can differentiate conductor and semiconductor. So conductor means they can easily allow flow of current through them, like copper, gold, these are the example. So what happens here in conductor, the bands are overlapped like this. Okay, this is your valence band and this is your conduction band, and you can see the overlapping is there. That means without providing any energy also, or even small energy you can give, the electrons are free and they can move inside the material, and when I connect any potential, then they can provide you current. So there is no requirement of providing additional energy here because both the bands are overlapped and you can have free electrons in normal temperature also. So a large number of free electrons are available in the conduction band, and conduction band and valence band are overlapped. A slight potential difference across the material causes the flow of carrier to constitute the current in it. For example, gold, copper, these are the material property. Okay, so that's why they are very good conductor. And another thing is very important here, this point, blue line I have drawn here. Conductor shows positive temperature coefficient of resistance. Generally in PSU you will get this question, or objective type you will get this question. Whenever we'll take a conductor and increase its temperature, what will happen? to its conductivity. Okay, so it says conductor shows positive temperature coefficient of resistance. That means what happens? Suppose I'll take a conductor here, and inside that lot of free electrons are present. These are the free electrons what I have shown, and if I increase the temperature, they'll move inside the material. So these electrons is moving this side, these electrons moving this side, these electrons are moving this side. So any random direction they will move. Okay, because I have not connected any potential here. If I connect the potential here, then the one side motion will be takes place. But as there are a lot of electrons are present here, and while they are moved, what happens? They will collide with each other. This electron will collide with this electron will collide with this electron. So when two electrons will collide with each other, what will happen? Some energy will released. Some energy will release, and that will also hamper the speed of these electrons, or movement of the electrons will hamper. Due to that, the current means the movement of electron, right? So if that motion or mobility is reduced, then current will also reduce. So current is reducing means what? The resistance in alternative way, if current is decreasing, then what can you conclude about the resistance?
Increase, sir.
Increase. If resistance will increase, then current will decrease. So,
Yes, sir.
Due to this repeated collision and lot of electrons are present, when we increase temperature, they will have more energy. We are providing energy means that energy will capture by these electrons, free electrons, and they will try to move. Suppose for an example, in a small place, lot of people are there, and some let us say someone has told that bomb, then what will happen?
So everyone will run.
Everyone will run. So during that process, collision will happen, and maybe that mishappening are unavoidable situation. So here also same thing. Lot of electrons are present. When temperature increases, collisions happens, and they will radiate or release energy. Due to that process, the movement will slow, and that's why the current will reduce. So current is reducing means ultimately the resistance of the material is increasing. So that's why it is shown, or conductor shows positive temperature coefficient of resistance, means when temperature increases, the resistance also increases. So that's why it is shown positive temperature coefficient of resistance. Is it clear?
Yes, sir.
Sir,
Yeah. Any question?
No, sir.
Okay, fine. So now we'll go for semiconductor. So semiconductor means it is just the conductivity level is very less or zero in insulator and very high in conductor. So semiconductor means the conductivity level is in between insulator and conductor. So if I represent those things in a energy band diagram, let us say this is the valence band and this is the conduction band, and this energy gap Eg is around 1 to 2 electron volt. So in you have just now we have seen conductor means overlapping, insulator means very high, semiconductor means it is just near 1 to 2 electron volt. So if we apply this small amount of energy, then we can able to remove these electrons from valence shell to the conduction band. If I am giving temperature, then these electrons will move from here to here. So the number of electrons will increase here, right? So conduction is possible. Okay, so it is neither insulator type or conductor type, so it will behave as semi. Semi means in between conductor or insulator. Now you can see those substances which have conductivity lies between conductor and insulator are semiconductor. Example: silicon, germanium, gallium arsenide, gallium phosphide. So these first two are simple material. and second two are complex or compound materials, gallium and arsenide, gallium and phosphide are taken, and the energy gap between this Cb and Vb, Cb means conduction band and Vb means valence band, are very less, that is nearly 1 to 2 electron volt. So very small energy is required to move these electrons from valence band to conduction band. Now the last point is compared to the first or conductor, it is just opposite. Semiconductor shows negative temperature coefficient of resistance. That means the example what I have given here, let us take a semiconductor here, and this is the energy band diagram. Now if T1 is the temperature, and after increasing the temperature I'll get T2. So if 3 electrons are present, and when I provide T1, then 3 electrons are moving from here to here. Now if I increase the temperature, that means what? More energy I am providing, so that more energy will capture by these valence electrons, and more number of electrons will go to the conduction band. Yes or no? Earlier 3 electron, now by giving T2 I am having 6 electron. Yes or no?
Yes, sir.
Yes, sir.
Now
Yes, sir.
the number of electrons will increase here, and if number of electrons will increase compared to T1 to T2, the conductivity means they will move inside the material and the conductivity will increase, just opposite of the conductor property. So in semiconductor generally, and if you ask that sir, in conductor if lot of electrons are there, then it is decreases. Here why it is not happening if number is increasing? So compared to conductor number, semiconductor number of electrons are less. Okay, so that's why even if the number is increasing 3 to 6, or for an example I am saying, it is not up to the conductor level, so it will not happen like that. Collision and energy loss will be not possible here, but it is seen in the theoretical practical scenario. So as number of electrons are increasing here by increasing temperature, then we can say the current is increasing. So current is increasing means resistance will decrease. So that's why the semiconductor will show the negative temperature coefficient of resistance. You can see here the semiconductor shows negative temperature coefficient of resistance. Clear?
Yes, sir.
Yes.
So whatever I have explained, that is represented in terms of energy band diagram. Insulator, you can see is high, and semiconductor and metal. Metal means it is conductor.
Yes, sir.
Okay, it is overlap here, or I can say also partially filled, and this is filled, and here this is the semiconductor, this is the insulator. You can observe here, this is the valence band, this is the conduction band. In insulator, the valence band is filled. That means lot of electrons are present in the valence band, but no electron is present in the conduction band. That's why I cannot move the electrons, because electrons are not present in the conduction band. How the current will flow, right? So generally you can say like that. In insulator, valence band are full and conduction band is empty. And semiconductor means though their valence band is full and conduction band is empty, but if I increase the temperature, then these electrons will move from here to here, and I can find electrons here in the conduction band, so conductivity will increase. And in case of conductor or metal, there is a overlap. That means if I look at from conduction band, it is half filled, and if I look at from the valence band, it is half it is also half filled, so partially filled we can say. So that's why we can have this conductivity, very good conductivity in the conductor. So with respect to energy band diagram, what we have discussed, we can differentiate this conductor, semiconductor and insulator. Next class we'll see our focus is on semiconductor. Okay, so we'll explain why semiconductor is important in electronics, why not insulator, why not metal, and we'll proceed with semiconductor, what are the types, what are the property, and all those things. Okay, so today's class, whatever we have discussed from the scratch, like atomic structure and energy level, energy band, and based on that different type of solids. If you have any doubt, you can ask me now. or everyone has understood everything? Has everyone has understood what I have explained?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
From the first class, I told you if you have doubt, you just ask me. Don't let your doubts pile up or confuse you in the later case. I'm ready to help you, but you have to ask. And as I told you in the last class also, every day after the class, just spend 10 to 15 minutes, just refresh what it is, where you are having a doubt, or you just recall whatever we have discussed, so that it will be helpful in your next class. Okay, so
Yes, sir.
next class we'll proceed, and next class means March first week. Let me first take your attendance. Just wait, don't leave the class. Wait for my instruction. I'll upload this material or PPT in the classroom. You can check there. After ending this class, I'll upload.
Yes, sir.
Okay, sir.
So can we leave?
Wait, I'll tell.
Attendance.
I'm taking the attendance. Okay, so I have taken the attendance. Now you can leave. Thank you for attending the class.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.